We're going to combine the concepts of vapor pressure and phase diagrams in tonight's vodcast. First, our definition of vapor pressure. When you look at any substance, no matter what temperature it's at, they don't all have inside the substance molecules having exactly the same velocity and therefore not having the same kinetic energy. Some have more kinetic energy than others. And when they escape the liquid, then they go into what we call the vapor or the gas phase. As you crank up the temperature, though, the fraction of molecules that have enough kinetic energy to escape the intermolecular forces that hold them in the liquid becomes greater. And that's what this graph is showing here. The red line represents the same substance at a higher temperature, and the dotted line represents the minimum amount of energy required for molecules to escape the liquid phase. So essentially what happens is that the area underneath the curve, which represents the fraction of molecules which have sufficient kinetic energy to become a gas, increases as you crank up the temperature. Well, we can measure this thing called vapor pressure by taking something like, say, ethanol, a volatile substance with relatively low intermolecular forces, and putting it inside a container with a manometer apparatus attached. What will happen is some molecules will begin to escape the liquid, and the pressure inside, as you can see, has now increased. But then what will happen is that over time, the rate at which molecules are leaving and going from liquid into gas becomes equal to the rate at which gas molecules enter back into the liquid phase. So you reach an equilibrium, and we call that the equilibrium vapor pressure, when the rate at which liquid molecules evaporate and vapor molecules condense are the same. Now obviously that vapor pressure must be directly related to temperature. And what you can see here is a curve of 3 or 4 substances that show an interesting thing when they cross this 1 atmosphere line. That's 760 millimeter or torr, the definition of what is 1 atmosphere of pressure. And you can say something is boiling when it is at a temperature that allows it to have a vapor pressure equal to the atmospheric pressure. So if I'm down at sea level, water will boil at 100 degrees. But if I'm up on Mount Everest, water will boil at about 72 degrees. So that's what we call just the boiling point. To standardize it and have something called the normal boiling point, you must specify the pressure which is above your liquid at that moment in time. And so therefore the normal boiling point of water is 100 degrees is a better statement. The reason why water boils more readily at Mount Everest is because you have like 5 miles less of atmospheric pressure pushing down on you and your Sherpa as you go to make a cup of tea. It'll start to boil at 72 degrees, but if you were cooking at high altitudes, you want to make sure that any food that might be cooked in boiling water, for example, is going to be fully cooked, and the way you compensate is by cooking it longer. Anyone who's a baker who's used a cake mix before, I guess you're not much of a baker if you're using a cake mix, but on the cake mix box it'll say high altitude cooking instructions. So that's what we call our vapor pressure curve. Now the vapor pressure curve is this part, segment TC, of what we call a phase diagram. And a phase diagram represents all the conditions of temperature and pressure at which a substance can exist as a solid, as a liquid, or as a gas. If you are in any one of these colored zones, not on a line, only one form of matter is present depending upon where you are. Notice that it is temperature on the horizontal and pressure on the vertical axis. Notice that if you are on a line, you being one of the data points, so if you pick a condition of X and Y, temp and pressure, that lands a point right on one of these segments, now you're going to have an interesting situation. For example, if you landed somewhere here on this slope, which is the line that represents the interface between solid and liquid, if you looked at your container, you would see both solid and liquid forms of matter. What's unseen to your eye is that the liquid is freezing into a solid at exactly the same rate at which the solid is melting into a liquid. And you could say that was true for any of the 3 major groups of phase changes on any of these 3 segments. So when you are on a line in a phase diagram, you are at equilibrium between two phases. Now, interestingly enough, here is the vapor pressure line that we were just looking at as independent curves. It starts here at this point called the triple point. And just like you would assume, the triple point means that there are all three forms of matter in equilibrium with each other. All six of those processes are taking place in opposite directions to each other, but at equal rates. So notice that there is only one x and one y, one value of temperature and one value of pressure at which that can take place. Now, what's interesting is that as you increase and move up this vapor pressure line, essentially what it's saying is as you get a substance hotter and hotter and hotter, you're going to have to increase the pressure on it to make it stay as a liquid until you reach something called the critical point. And after the critical point, it turns into this thing called a critical fluid. So let's take a little bit closer look at that. The critical point is defined as the critical temperature and critical pressure. What that means is that this point C has a critical temperature directly dropping down below it and hanging a left a critical pressure. And after that critical temp and pressure at the critical point, you can't really distinguish the liquid and the vapor from each other. It becomes this interesting thing called a supercritical fluid. Normally, if you were at ordinary pressures and you were above the critical temperature, then you would have just an ordinary gas that behaves the way that we've learned in our gas laws unit. But if you are at extremely high pressures, like hundreds of atmospheres, and also above this critical temperature, you've created this thing that's called a supercritical fluid. And a supercritical fluid is sort of like a gas in a way in that it expands to take up its container, but its density is more like that of a liquid. And very interestingly enough, in your textbook on, I think, page 453, you will see sort of a green way of how we decaffeinate coffee using, I believe it was carbon dioxide gas in a supercritical form. So that is our critical point. Each point along that line is the boiling point of a substance at whatever specific pressure that it's at. So remember, that's our vapor pressure curve. Here is the line that represents all the temperature and pressure points at which it represents a liquid and a gas being in equilibrium with each other. Now, normally what happens, you can measure the pressure, the melting point at each pressure along the line. And normally what happens is the line looks like this for most substances. It has a positive slope. And the reason why that it has that, make sure I'm checking my notes here so I'm saying it correctly, is that for most substances, the solid form is denser than the liquid form. And usually if you increase the pressure, which is what I'm doing as I move up the line, it's going to favor the more compact form of a substance. And usually if you're going at higher and higher pressures, you're going to need higher and higher temperatures to be able to get that substance to melt. And that's why this line would have a positive slope. So let's look at what our buddy water does. Let me skip ahead here to find that. Notice that water has a very interesting slope here, where it slopes back and to the left. It has a negative slope. And water is very exceptional because its melting point is actually decreasing with increasing pressure. That's why it's like tilted back here and to the left. And again, remember we said that increasing pressure favors the more dense form of the substance. Well, the more dense form of the substance in water is liquid, not solid. And that's because as they form hydrogen bonds, they expand out. I think they bond to 4 other water molecules, leaving a lot of space in between them, creating a less dense form of matter. So that's why this blue area that's encompassed here, where water could act as a liquid, is actually getting larger, not smaller, relative to most other substances. Remember, water has hydrogen bonding, and so water has a very high critical temperature and critical pressure. In the slide it says it's because of stronger van der Waals forces, but let's make sure we understand we're talking about hydrogen bonding. And again, once more, Water can exist as a liquid at surface temperatures and surface pressures because of this, and in doing so allows life to exist, because our life on this planet anyway is based upon a soupy ionic slush of water being the solvent for many other biomolecules and ionic substances necessary for life. So backing up again here, let's take a look at this triple point. Below the triple point, a substance can't exist as a liquid. So down here, I'm not sure what that's meaning there, but above below the triple point, a substance can't exist as a liquid. So notice that if you're looking at just the segment right here, you can only have solid turning into a gas or gas turning into a solid. Let's take a look at carbon dioxide. I hope they put up a slide of that so we can take a closer look at CO2. It has an interesting thing going on. So here's that negative slope of water, and as pressure is being increased at a temperature that's just below the melting point, water will turn from a solid into a liquid. So melting point of water is going to decrease with increasing pressure, and the more dense form or condensed form of the substance is being favored as pressure increases. That's why the amount of liquid water blue area is larger. Many of you have either played with dry ice, or I know Ms. Hackworth does a lab where she has dry ice in the punch. And dry ice, I hope you know, is not really ice. It's frozen carbon dioxide gas. Now, to get it to freeze, you got to get to 100 and something below zero to get it to liquefy and then to freeze. And interestingly enough, when you put the CO2 on a desktop, the dry ice, and a little chunk of dry ice, it seems to disappear in front of your eyes. That's because it's subliming. It doesn't have to melt. You won't see a puddle of liquid CO2. If you did, it would be really, really cold in that room. And also very high pressure. So let's take a look at what's going on here. Notice that the triple point of of CO2 is pretty high. It's saying that its triple point is at minus 56.4 degrees and at 5.11 atmospheres. Above the triple point is when you can have the possibility of it existing as a liquid. So if you feel the pressure that's on your sinuses in your head right now, you would have to increase that by 5 times to be squeezing hard enough on CO2 molecules to get them to crowd in together and behave as if they were a liquid. So that explains why carbon dioxide can't exist as a liquid if the pressure is anything above or below 5.11 atmospheres. And this was the supercritical solvent. I'm not even actually sure what that's showing, but if you read that section in your textbook about the decaffeination of coffee and how they use it as a really good solvent that can extract a nonpolar substance like caffeine without having any leftover toxic chemical waste problems, it's kind of interesting. So that will bring us to the last section of this chapter, solids. And there will probably not be a vodcast on solids. That is because you will complete a reading worksheet which will take care of understanding the small amount of information about solids you'll be responsible for. Take care. I will see you in class.